All right, so good afternoon. So a couple things that I work on all year long and try to add to this presentation are all the little hiccups and tips and tricks that I can find for multibeam, LiDAR, anything that I think is important, people should be aware of, that you'll potentially run into. And I like to see it when I see light bulbs go on over people's heads going, man, that's the problem I've been running into. So just trying to help you avoid any of those disastrous type things, because sometimes you travel hundreds and thousands of miles. We had a client that traveled 1,500 miles in Canada one time, did not review the data before they left the site, went back to their office and found they had a problem. All right, so these are the things we want to try to avoid. All right. So first thing, and you've been hearing some of these things already, but I'm just kind of going to round all these up in this presentation, your setup. All right, the one thing that I cannot stress enough is the stability of the mounting bracket or pole of the sonar for the multibeam. Typically, what we try to stress is the 2 points of connectivity to the vessel. Whether it's a side mount, a bow mount, a through hull, moon pool, that it is as rigid as possible. And I know the guys that build the USM brackets, the Universal Sonar Mount, and the ones that's here, not that I'm downgrading what they build, because the material and every way they machine it is great. I just don't like the 1 point of connectivity. Basically, if this is my mounting bracket and this is my pole, basically this is what's going on with those brackets. I have 1 point of connectivity right here and 1 point of connectivity here. But if I've got this sonar, and is Pogo in here? Okay, great. I know you know all about this. All right, so the Jacksonville district over in Tampa has a universal sonar mount. They called me up, and it's been at least 2 years ago. So, I mean, these brackets are very heavily built, and I have nothing against that. It's just with the 1 point of connectivity, how tall is the gunnel on your boat? Above the water. And then how much further is the sonar below the water? 4. So think of a 9-foot lever arm that only has 1 point of connectivity here. It's got an 80-pound sonar hanging on the bottom, and anytime they got above 5 knots, this is what's going on through the water. And there is nothing that is going to compensate for that. I don't even care if the IMU is on the sonar head. This is a high-frequency vibration below the water. It's not rolling, it's not pitching, it's a side-to-side movement. All right, the only way that I know to correctly solve for this is to add a secondary stabilizing arm down low near the water. Now I've shortened the lever arm, I have 2 points of connectivity, and this isn't going to go side to side like this. So the more rigid you can make the sonar mount, the better. And you don't want any movement. And even these very simple ones, we can see here, point here, and it's about halfway through the total length of the arm. So this is going to be very stable here. This is another one. Point of connectivity here at the top of the gunnel, and down as low towards the water line as they could make it. So these are very stable types of brackets. Another 2 point connectivity where they physically welded or bolted on a bracket down here so that when they put this on, it's got 2 points of stabilizing access points for the mounting bracket. Again, probably the most copied side mount bracket is this. I think industry-wide it's known as the Reese On side mount. Reese On came up with this back in the 90s. It's a very simple U bracket here with a disc welded to a stub arm that's welded to the main arm. All right, it's got another very similar disc with the stub arm welded to the main pole, and this rotates up into this one. And if you can see, there's a little dot right here. That's a hole that has a matching hole on this disc here, and it's the size of a number 10 screw. So you just go to Walmart or Lowe's or Home Depot, buy the cheapest pot metal number 10 screw you can get, and you run it through the disc here that runs through this plate. You put a nut on the back side of it, and if you hit anything with the sonar, it simply shears that bolt and kicks the whole system up. Don't damage the mount, don't damage the sonar, and it works really well. So another point about stabilizing this, and we probably have a few overseas people here, but there's a gentleman by the name of Duncan Malleus over in England. He's probably one of the most well-known multi-beam surveyors over in the England area. And he actually got invited by Reese On to come do a talk at their users group meeting, and they posted this on their website. I sent an email to Duncan, asked him if I could use bits and pieces of his presentation. He said, by all means, please do. So if you get, let's listen to what he has to say here. Oh, don't tell me it's not going to access.
We have a two 7125 system on here. So we have one 7125 on this pole, and then there's a similar setup on the other side over here. And getting your pole right with your pole mounting stuff that is not hole mounted is absolutely essential. You cannot beef up your pole anymore.
So I'm going to stop it right there. But if you can see, this will work. So see the little skinny pole here? That's what they were given to mount a Reese On 7125 to. See the big pole he's got here? That's what he replaced it with. All right, because they're running a 7125 on each side of the boat. They're running dual 7125s on this, one on each side of the boat. And that little scaffold pole is what they thought they could mount the 7125 to. And he said, forget it, that's not going to work. This is what you're going to have.
So we just got a large amount of tubing and structure to it, and then you've got to make sure that that thing fits well to the side of the boat. If the pole moves, you're on a hiding to nothing, you're going to have bad data, there's no doubt about it. So you need to be as good as you possibly can.
All right, so again, same thing happened recently. It was last spring. Got a phone call, customer working out in the Gulf, and they sent the data in. I could tell the pole was moving. I told them the pole was moving. They didn't believe me. They flew me down. I got on the boat, and I said, are you sure the pole's not moving? And this is one of the units, this is a USM universal sonar mount. Again, just a single point of connectivity up here. And you can see this is like a 12-foot lever arm. All right? And I said, I'm telling you, the pole's moving. No, pole's not moving. Really? So while it's up, I had to move this stub arm out of the way, and I just reached over to the side of the boat and gave it just a quick little push. The camera is not moving. And okay, that's in the air. Imagine when it's in the water. This is a 90-foot boat. When it's moving 5 knots through the water, the hydraulic force that's going to be applied to that pole, it's sit there and it's doing this through the water. So they said, we still don't believe you. So okay, well, let's put it in the water. All right, so we put it in the water. I did the same thing. That thing's not moving side to side? Really?
How long is that pole?
12 feet.
Oh, yeah, you can't expect it. That's not a high frequency motion.
Yeah. So so even if the IMU is on the sonar or on the pole, what's changing is the relative offset arms to the primary GPS antenna. So the antenna says, I'm not moving. The IMU says, I'm doing this. So it's trying to compensate and move all the positions. Right, and the data showed it. And so they literally took me right back to the airport. I got on a plane, came home. But their suggestion was, what do we do? I said, you need to either bolt or weld something to the side of this boat. And the company that owned the boat said, you're not doing that. Yeah, matter of fact, I think they even build one now. It's real simple. It just needs to be like a C cup like this, that its ID matches the OD of the pipe, and then it comes over and somehow locks on the side of the boat. It's more a side to side than it is a front to back. The front to back is typically never the problem. It's the side to side movement. Yeah, but even if you would do it, that's only going to support one side flex. Because if it doesn't secure to the side of the boat, it doesn't have anything that keeps it from swinging away. But it would help to one side, it's not going to help to the other side. The other possible option would be if you just put a flip down type stub arm on the pole, is to run a ratchet strap under the hull. But, okay, well, it might be ugly, but if it works. Right, but it's better than what this is. So this is, like I said, I have nothing against the manufacturer and the way this is built. It's the fact that it only has one point of connectivity. All right. Another great advantage to have is a tilt bracket, where you can physically rotate the sonar itself. All right, so this screen capture is from a Reese On 8101, which is a 150-degree system. We put a 15-degree tilt, physical tilt on the sonar, so that it's now running and shooting almost as parallel to the water surface as possible, and able to get all the way to the water's edge as close as possible. And the great thing about this is it keeps the boat and the sonar out here in the deep water. All right? Because if I have to keep the sonar in a straight down mode, then it may take me 3 or 4 passes in the straight down mode, and now I've got the sonar over here. And if there's some kind of submerged object that I cannot see, and I can tell you, I've knocked the sonar off the boat 4 separate times. Completely broke, huh? Not when it looks like chocolate milk. Yeah, no. And believe me, on a 30-foot boat that's 8.5 foot wide and my sonar is only 12 inches wide, I guarantee it'll be the first thing that finds whatever's under the water. Every time. And so if you can use a tilt bracket, that allows you to keep the boat out here in the safer, deeper water and shoot as close to the water's edge as possible. And then do it in one pass instead of 3 or 4. And keep everybody safe, not just the sonar, but the whole boat in general. All right. The other thing, too, when you use a tilt bracket to be aware of is you have to set a range in the sonar. All right. So the range, meaning the range is, if people that don't know, the range is the distance from the sonar along the outer beams, the outermost edges. Not what's directly below. It's not a depth thing. It's the distance that the outer beams have to travel along their widest angle. All right. So if you put a tilt bracket on, the one thing that the sonar's like is to be uniform on the distance that each side has to travel. If you're really close over here and the sonar's sitting right here, then you're really short range on one side and a long range on the other. And the sonars don't like to have to listen. Well, one already got a return and is still waiting for the other side to get a return. So if you can keep it where you're out here at the same range distance to both sides. When it's tilted this way, the sonar will react much better, get you cleaner data, and just work much better because it's listening to the same amount of distance for both sides. So you're seeing this screen right here, and you just kind of guesstimate and says, well, this distance looks like about the same as that distance, and it's going to work pretty well. Yeah, I usually try to say if you run somewhere near where the toe is, you're going to have a same range type thing. It just depends on how severe the slope is along the bank line. All right, and this is how simple it is to build a tilt bracket. So you've got these two bolts right here, and typically what on this particular setup, you would just loosen this bottom bolt, and you would pull this bolt all the way out, and this one has the ability to tilt left or right. And these holes, even though it doesn't look like much, that's 15 degrees of change between those holes. So as I showed yesterday in the hardware setup for the Multibeam, you can load multiple instances of the same device where you'll have an instance where it's in the straight down this way, and then you'll have an instance where it's maybe a 15 left and a 15 right with all the differences in the offsets for the starboard and vertical and roll. And then do your patch test for all three setups. And then when you need to use one of them, you bring it up out of the water, make the physical change, go into hardware, disable one, enable another, and you're ready to go. So the other thing too is when you drill these holes, drill them to the tightest tolerances that you can that match the size of the bolt. Do not oversize these holes because now you're creating a wobble that the bolt can have, and it may not get to the same exact roll alignment if you've got a little play in those holes. All right, this is the bracket that I had built when I worked at the Corps. And if you can see here, you can see there's dark circles in these holes. Those are actually stainless steel inserts that I had them put in this flat plate. And when it was in this orientation in the straight up and down, I had them tack weld these two pieces together and then drill the hole straight through and put the stainless inserts in so that these holes only lined up perfectly. I had them then cut the tacks, tilt it 15 degrees, tack it again, re-drill the holes, put the stainless inserts in, and I spent about $5,000 having that little 3-foot stub arm built. But, what? That's an 8101. And so now I felt very confident that when I loosened this bolt, pulled these two bolts out and rolled it to the left or to the right and screwed it back in, that my offsets for my patch test values didn't change because I knew the way that this was machined and put together. I did a patch test anyway just to have it in my hip pocket, but they never changed. All right, this is a new feature that I put in this year. I talked about it last year, but I wanted to go ahead and give some more graphics to it. So the convention of offsets, starboard and forward versus X and Y. All right, HYPACK convention, we tell you what we want. Starboard offset, vertical offset. Most every inertial system wants the X, Y, and Z. All right, now the question is, what's X? What's Y? What's Z? Which direction is positive? All right, in HYPACK, we're starboard positive, forward positive, vertical down positive. All right, that's our orientation. I pulled the next three visuals completely straight out of the inertial manual for the device I'm getting ready to show you. So for the Novatel, they are X, Y, and Z offsets. So X is their starboard, Y is their forward, just like we are, except Z is positive up instead of positive down. So HYPACK is like this. They're like this. Okay, that's the Novatel's. And again, I copied these straight out of their manual. All right, the next one is the Aplanics. All right, they are X forward, Y starboard, and Z down. So they're like this. Except, well, except this is X and this is Y. Instead of HYPACK, this is X and this is Y. Okay. All right. This is the ICSI. They're X forward, port positive, and Z up. So they're like this. So please read the manual for the devices that you have, because everybody's convention is not the same. I really wish everybody would change to starboard, forward, and vertical, then there's no question. But when you're X, Y, and Z, you better read the manual to understand which direction that is and which direction is positive. All right, the other thing too is in HYPACK, what units are you in? Well, we're in the units of whatever your project has been set up in. Almost every inertial system, and I have nothing against this, but because most of the inertial systems come from out of the country, but almost every one of them uses metric, right? We're in the US right now, and everything goes by US survey feet, which from what I understand is going away. We're going to be going to international feet. Huh? No? Nobody's heard this yet? Okay. All right, and does everybody know what the difference is decimal-wise? 7 places. Yeah, so the U.S. survey foot is 0.3048006096 as a conversion from meters to feet. International feet is simply 0.3048. Right? So you have to go to the 006 as a difference. And that doesn't sound like it's going to make a difference until your coordinate units get into the millions. All right? It's 23 feet if your coordinates are in 10 million. Yeah. A 23-foot shift because of 7 decimal places over and your units are in 10 million. All right? So I'm not sure when that change is going to happen, but that's why we've got the ability to do U.S. survey feet or international feet. And more than likely, whenever the states do adopt this, we'll probably change the default units for all the state plane coordinates. But right now, there is 2 states that I'm aware of. South Carolina is one, and I think Oregon or Washington, something in the new Northwest, I think, has it as well. Arizona, okay. But anyway, 2 of them have adopted it years ago, but we may all be going to it here in the States. But again, make sure, and that's going to be, this is going to go back to my inertial systems here, is in HYPACK, the units are always whatever the project is in, but the inertial systems are always typically going to be in metric, and Aplanics is really good because they put that little, right here, they put the little meter sign right beside it to let you know, make sure you enter it in meters. But what you don't want to do is, usually the first thing you're setting up is the inertial system. And you measure and convert all the offsets to metric. And now you go into HYPACK and you're in the US survey foot and you go, what was the starboard offset for that? And they call it out in meters and you enter it in meters. Now you're off by a factor of 3.3 of what the true distance is that you should be entering in. But luckily enough, if they're in HYPACK, we can fix it in the editor. So that's not a problem. All right, this is another thing. When you're measuring, make sure you understand what your tape measure looks like. If you don't, shoot them in with the total station. Because you look at this and go, well, where I've got the little red arrow, what's the correct number? Is it 10.56, 15.6, or 1.056? Am I kidding you? No, I'm not kidding you. Don't get me started on the metric system. Yeah. Again, Duncan Malleus from the UK, this is another video capture from his demonstration talking about, you know, the rigidity of the pole and movement and offsets, and I think this is really important.
One of the first surveys for the old 8125 did, this was really what started using Multibeam for marine archaeology. And it's also a good example of a bad data or problem you have when you haven't either measured offsets properly or you have a moving pole. Anything that goes in the same direction as a survey line and is considered as constant, if you like, is not part of the seabed. That's been introduced into the data by some misalignment error, calibration error, or physically the pole moving. So if you see anything like this in your data, then you need to get rid of it, and you'll find out what's causing the problem and get rid of it, because it spoils it. So that's what the 8125 was like. And then when we had the 7125, and this is the same as the serial number, it was not number 1, it was number 2. And this is also now looking at point data, and you can see there's none of these, we call it cloud field effect, so none of the humps in the data. This is equiangular, so that's where you get more spacing on the outside. But another top tip, don't ever do wreck surveys with equidistant spacing.
All right, and I'm going to stop it right there. So you're going to hear that these systems also have what they call equiangular spacing and equidistant spacing. So what he's pointing out is you can see on the outer beams here, the outer beams are starting to spread apart because they're on equiangular, all right? And what he's saying is also if you ever do a wreck survey, don't ever do equiangular because, what? I'm sorry, you're right, don't do equidistant. Because the equiangular, so if we hit a vertical wall, equiangular, and now some of the sonars I've been told are doing something different with the way they do equidistant, that equidistant typically says, what's my nadir depth? And let's say it's 10 feet. And let's say I've got the sonar set to 150 degrees, which is 7.4 times coverage. So 7.4 times coverage means I'm going to get a 74-foot swath in 10 foot of water. All right, and just to make numbers simple, let's say I have 74 beams. All right, that's going to space every beam 1 foot apart. That's what it's going to try to do. Well, if I hit a vertical wall, how does it horizontally space beams 1 foot apart when they're equidistant when this is a vertical wall? It can't. All right, now I know there's some high-powered math going on a lot of the newer sonars, and maybe they figured out a way to get around that. All right, but you'll have to talk to the manufacturer and get them to verify that. But typically, this guy who, like I said, he's one of the best in the world, and if he says it, and he's at the Reese On Users Group meeting, and even in the Reese On manual, which I usually have a slide of, it will tell you, and I don't think I did, no I didn't. It will tell you that for flat bottoms, that's when you use equidistant. For significantly changing terrain bottoms, you should use equiangular. All right, and there was something else in here I wanted him to talk about.
Point data, and you can see there's none of these, we call it cloud field effects, so none of the humps in the data. This is equiangular, so that's where you get more spacing on the outside. But another top tip, don't ever do wreck surveys with equidistant spacing. It's just horrible. So equiangular, 256 proper beams. None of this made up extra beam malarkey. 256 proper beams, and you get good quality results.
All right. So again, just some tips about, you know, when you're collecting your data, usually what I like to say about a multi-beam survey is, you know, people would say, Joe, if you were going to buy a multi-beam system, which one would you buy? Well, the way I look at it is I'm going to go to my toolbox and I'm going to pull the best tool out of my toolbox to do the job that's required. Everybody familiar with Harbor Freight tools here in the States? Okay, Harbor Freight tools is like the Walmart of cheap tools. And I'm not going to go to Harbor Freight and buy a $2 hammer to re-roof a 3,000 square foot house, all right? Because I'm going to be back 50 times to buy 50 more hammers because I'm going to break that $2 hammer. I'm going to go and I'm going to buy the $150 hammer and do the job with the right tool the first time, all right? So I wish I could tell you there was this all-in-one perfect multi-beam system that does everything you think you'll ever do. I just don't believe it exists, all right? So I tell people, read the end of the book or read the end of the scope of work that says, we want this as the final product. 1 foot space data, half foot space data, 5 foot space data, 10 foot space data. Okay, what is the end result? Now I know what hardware I need to go pull out of my toolbox, set up on my boat to collect the data. I know how I need to collect my data. Do I need a 10% overlap, 25% overlap, 50% overlap? Because I want to make sure that I've got covered what they're requiring. And then that's going to help me do the processing side. Do I have to really meticulously process this data, or they just want something quick, fast, and in a hurry? All right? So knowing the end product will tell you how to do everything from the start to the finish. All right? So that's the one thing I'll say about as far as the equipment goes. Again, the stability of the sensor that we just saw, knowing how the offsets are measured, what directions are X, Y, and Z, making sure you get all that right, because the term GIGO, G-I-G-O, garbage in, garbage out. All right? If you don't do all the stuff right on the front side, you're not going to get anything good on the other side. So, well, the other things that we run into quite often is the communications between the equipment and the computer. Firewalls. How many people have IT departments you have to deal with? Yeah, nobody wants to raise their hand about that one. Okay. Because they have all the admin control on your computer. And the one thing they're not going to turn off are the Windows firewalls. Dave, how often do you run into Windows firewall problems? All the time. And this is with a single beam. Yeah, the Mark IIIs and the CV units, I mean, all the time. They're network connected. And the one thing that the IT people have done is turn the firewalls on. As soon as you turn the firewalls on, data comes in with no problem. All right? So make sure you go into the control panel if you have admin access. If you don't, get them to come in and turn it off. Pat Sanders, the founder of HYPACK, one of the things he professed was the survey computer should be just that, a survey computer. It shouldn't be accessing the internet and checking your email and everything else. It should just be used to collect your data. All right? So there shouldn't be any firewalls turned on. It should let everything freely come into the computer and do what it's supposed to do. All right? So just one of the things to look at. Again, communications, talking to the device. Basically, it's what is the phone number for a device so that you can get the information from. How do you dial into it to get what you need? All right, so knowing the correct IP addresses. So again, pulled this straight from the Applanix manual. They tell you very clearly, Applanix sets the IP address of the PCS to 192.168.53.100. Subnet mask of 255.255.255.0. Initially communicate with the PCS, you must give the controlling PC a unique address. I'm going to show you how to do that with the same subnet mask. They even recommend what you should set it to, 192.168.53.101. All right, to do this, you have to go into your control panel, go to your network and sharing center, click on the change adapter settings, then right-click on your local area connection, click the properties button. Again, multiple steps to get there. All right, go to the IPv4 like I did this morning when I connected the laser up. Instead of obtain IP address automatically, we're going to tick the box that says use the following IP address. Since Applanix told us what they would recommend, I'm going to put that in, 192.168.53.101, with the same subnet mask that the PCS has. Great. What happens if I've got multiple devices that connect through the network to my computer? And I took the network switch back that I had. But if I've got a network switch, and I've got a POS-MV plugged into it, and I've got the Odom Echo Sounder CV plugged into it by network, and I've got my Multibeam plugged into it by network. I might have something else that plugs into it network. All of these have individual IP addresses. But I'm plugging into a switch with 4 different devices, and it's plugging into the computer with one connection. I just set the IP to that connection to 192.168.53.101. R2 Sonic has 10.00.86. The Odom doesn't require an IP, but maybe I've got another device that does. Oh, I've got the laser, which is 192.168.1.201. All right? So I need to be able to talk to all these devices through that one singular connection. Again, I'm going to go into the Network and Sharing Center. I'm going to change my adapter settings, go right-click on the local area connections. I'm going to click on the properties, get back all the way into the same point that I got to when I set the IP for the port. But now I'm going to click on the Advanced button in this window. And in the Advanced button, this window is going to pop up. I'm going to say, I want you to add the ability to talk to these other devices. All right? So I click the Add button. This little button pops up that says, what's the IP address in the subnet mask? 10.0.1.102. That's going to be for the R2 Sonic. I'll hit the Tab button. It's automatically going to set the subnet mask. I hit Add. If I need another device to add, I'm going to hit the Add button again. And maybe I'm going to add the 192.168.1.201, or actually it's going to be 177, for the laser to talk to. And now I'm going to have 3 possible addresses that this one port can talk to. All right. Once I'm done adding all the extra IPs, I'll click the OK button. And now all 3 of those devices coming into the switch with one connection coming into the computer will all talk to the computer. We've actually had a user in Canada that had a POS-MV, a dual 7125 multibeam, and 2 HDL32 LiDAR systems, all running simultaneously through a switch into the computer. Now, they did tell us that about every 15 minutes, the computer crashed. All right, and at that time, when Dave Maddock was our head of programming, I presented him with the problem, and he started laughing. He said, Joe, he goes, all the data's getting in there. He goes, that's not a problem. It's when it hits the hub inside of the computer that you've got you've got the POS-MV that's bringing data in at 50 hertz for position, motion, heading. You've got 700,000 points per second coming from each of the 2 LiDAR systems. You've got multibeam data coming in at probably 10 to 20,000 points per second. He goes, it doesn't surprise me that it's not dropping packets all the time, because literally the network card cannot handle all of that. Even with solid state drives and everything, it's just too much data for the computer to handle. Yes? I've never tested it past 4, so I can't say for sure. I would imagine it can handle. I mean, I was on a boat, the Egyptian Navy, and we installed a 32-port NIC board in. We never hooked 32 things up to it, but it was there. So I'm assuming if they make that a 32-bit or 32-port network switch, it can bring it into the computer. Again, I believe briefly showed this yesterday, talking about the data collection and the hardware setup for Multibeam. Inside of the documentation folder under the last year or two's versions of HYPACK is where we have the high sweep interfacing notes. And again, I'm I'm on a mission to update that so that I'm including the devices software setups so that it makes it a lot simpler, because we can say, well, this is what you have to do on the HYPACK side, but I'm trying to help show what you have to do on the devices side as well. Because if you don't set them up to tell it to send the data to us, then we're just not going to get it, even if you've got all the right IPs and port numbers set up. All right, calibration. I know Mike went over patch test today, but one of the things I just can't stress enough is verify your offsets. Make sure you didn't transpose a number. You measured something that's supposed to be 3.56 and you typed in 5.36. It's very easy to do that. Patch test, the importance of positioning is more crucial than most people realize. If you can do it with RTK, that's the best way to do it. If differential is the best positioning that you'll have, then that's fine. But just to give you an idea of how crucial that is to look at this. If I believe that differential positioning is sub-meter in its accuracy versus centimeter in RTK, if I have a 1 meter or 3 foot error in my positioning system and I'm in 40 meters of water, or what, about 13 meters of water, if I just do the quick math on this, I can introduce up to about a 4.5 degree error in my pitch and my yaw offsets. All right. So again, the moral of the story comes down to, well, if differential is the best I can get, are those patch test values good? Well, absolutely they are, because if differential is all you'll ever have, then that's the best you can do for isolating what the angular offsets are. But if you can do it with RTK, at least the first time, do RTK positioning, you'll get much better angular resolution on it. Then just use those values even if you do the survey with differential, because the better positioning said this is what the angular offset should be. So I'm going to use those values even if I'm going to do a worse positioning correction system. All right. Another thing that will happen is we get users that are doing their best to do their due diligence before they leave to go on a job site. And so they'll hook everything up to the computer and they'll test it, and they get this thing called like an A cosine error or A tan error. And they're like, they call us up and go, what's wrong with HYPACK? How I'm getting this error? I'm talking to everything. Well, typically it's because they've hooked everything up, but it's laying on the ground sideways. All right, just like I've got the drawing here. And the MRU is reading like an 88, 90 degree roll or pitch value. All right, programmer put a trap into the device for the MRU that says, if it's more than 45 or 60 degrees, send an error because I don't believe the boat is running like this. And, you know, so Bruce Francis, who used to be with Applanix, I was asking him one day, I said, Bruce, I said, how good is the pause? I said, is there a point that it can't compensate for the motion that it's experiencing when I'm out on the water? And he looked at me, he goes, Joe, he goes, you'll get off the boat before it can't handle it. So, okay. So these systems are very good, but again, we don't believe that you're running a boat sideways like this and trying to collect multibeam data. So if you ever see this A sine error, A cosine, A tangent error, then that's typically what it means is that one of the values, roll pitch or typically roll or pitch, has exceeded a 45 or 60 degree angle. And as soon as you put it up right, that error will go away. All right, I added a few screen captures to this from the last time. Yes?
Sorry.
No.
Just in terms of the pitch and roll, you make an echo sound and it has a MRU inside.
Sure.
And it does kind of real-time correction of the swap.
Right.
Is it necessary then to disable, and is it something you need to disable the roll so that it doesn't get a flag twice?
No. A flag comes through from the sonar telling us that it's already been pitch or roll corrected. That's right. Yeah, there's a flag in the data packet. Yeah. So A couple years ago, well, right, probably about the 2016 timeframe, we got a lot of phone calls about people using AMLs, and they couldn't figure out why their depths were about 100 feet deeper than they should have been. And what we found out after talking to AML is that they put in a new selection for the output. They called it HYPACK 2015. And reasonably understandable what they did. They said, oh, well, if you're going to be working in a feet project, then we'll just output the HYPACK VEL file in feet as well, the depth in feet and the sound velocity in feet. What they didn't know is ever since the beginning of time of HYPACK, we always store everything in the actual text file, in the ASCII format file, where the depths are always in the units of your project, but we always, always, always store the sound velocities in meters per second. It's a rounding issue thing. The reason they did it, because the sound velocity probe measured it in meters per second. We're just going to hold it that way. When you bring it into the editor, then we make the conversion, so we're not making multiple rounding issues back and forth. So when they saved it to feet per second, you know, let's say, so 1,500 meters per second is 4924 feet per second. What was happening is when they stored that column that way and they brought it into the editor says, oh, I know the VEL file has the sound velocity in meters per second, so we automatically multiplied it by 3.280833333, and now you get readings like this of 16,000 feet per second was the sound velocity, and your depths end up being about 100 feet deeper than they should be when we apply that sound velocity cast to it. So just be aware, if you've got an older AML and it still has the 2015 selection, do not use it. Data collection, again, I kind of suggested this already. Know the final product that is expected from you. What is the accuracy, the data density, coverage, overlap? You know, is there a timeline that you're being held to get this? Because then that will tell you what equipment I need to use, whether it's high resolution or not, how to collect the data. Can I get away with a 10% overlap, a 25% overlap, a 50% overlap? Two suggestions I'll give you is, if this is post-hurricane and the Coast Guard wants to know, is the navigable channel clear? Minimal to 0 to 10% overlap is all you need, because they just want to know, is there any debris in the navigable channel that's going to be a hazard to navigation, all right? But now if I'm doing any other type of survey, even if it's a project condition or if it's a dredging survey, which does require the 50% overlap, at least by core standards, I'm going to do a 50% overlap. Because that way, if I'm here and then I just move over to the outer edge of this swath with my next pass, I'm getting 50% overlap on the previous one. And if I want to chop 5 degrees off of this one and 5 degrees off of this one, I still have overlap between those two passes. It just makes the processing a whole lot easier, and it's going to create maybe a minimal amount of time extra in the field to collect the 50% overlap, but I'd rather have more than less. Because the last thing you want to be able to do or have to do is go back. When maybe you only had a short window to get in to do it anyway, do it right the first time. All right? Again, knowing the final product also tells you how to process the data. Is my final product a 1 by 1, 2 by 2, 5 by 5, 10 by 10, 20 by 20? All right? Are they expecting the minimum, the maximum, average? What are we looking for here? All right, so that tells you how meticulously or non-meticulously you need to edit that data. All right, do your best to plan and prepare prior to the survey date as much as possible. This is a rule of thumb that we follow here at HYPACK is when we know that we've got to go on site to do training, we like to have at least 2 weeks notice, because I'm going to call Ken and go, Ken, what are we doing in 2 weeks? All right, what do I need to train for? What do I need to prep for? Is there anything I need to bring extra? What am I looking at? And Ken's going, oh yeah, we just got this brand new sonar system and we haven't hooked it up yet and we're going to need your help. So I'm on the line to the manufacturer and I'm going, tell me what types of connections you got. BNCs, serial, network, what special adapters might I need? Because now I'm on Amazon and I'm buying everything I think I might need, because when I get out in the field, there's not a Radio Shack around or anything, and if I don't have the right connection and I'm not able to talk to the piece of equipment, I can't do anything. So, you know, do your best to do your due diligence and plan, you know, determine your necessary equipment, assemble, try to test everything before you leave, calibrate it if possible before you leave, and again, pre-plan your survey data collection. If there's any old survey maps, anything that's got contours, so you can get an idea of how long is this really going to take me. You got a question, Donnie? Okay. You know, can I use 90, 120, 130, 150? What swath width can I use? Once I know what one of these swath widths are, I can kind of determine what my overlap's going to be and how long it's going to take. Inside of HYPACK, we got a nice little routine where if you tell us how long the lines are and how many you're going to run and how fast you're going to run, it calculates out how many hours it's going to take to do the survey, based on the information that you tell us. So it'll help you pre-plan for what you've got to do. All right, couple different strategies. I've heard several people already say this this week. Start in deep water and work towards the shallows. Shouldn't be hitting anything in the deep water, and you know, work towards the shallows are great for obstacle avoidance. Another thing that's great for obstacle avoidance that I've already shown you is using the tiltable mount. All right, to me, I think that saves tons of time and is a safety issue and will give you almost all the way up to the water surface. All right, processing. One of the things, you know, we've talked about this new auto pre-processing feature that we've added into the MBMAX 64 program to potentially get you closer to the final product as soon as the survey's over. I'll just tell you right now, I'm not a fan of auto processing. I think there's too much black magic that's going on in the background. I saw David Wells about 2 months ago at the University of Southern Mississippi, sitting in his office, and we were talking. And I said, you know, I use page 4 out of your cube manual all the time. And that's why I put it in here. And this was written by him. It says, the last point is very important. CUBE, which stands for Combined Uncertainty and Bathymetric Estimator, where the E is the key, is by definition not a complete solution to the hydrographic processing problem. It will not ever replace completely a human operator. And I think this abides to every auto processing program on the market. The goal is to provide a power tool to assist the operator, and I think this is the most key word in editing data, is interpreting the data. All right, I've got 60, 70 people in here right now. If I gave all of you the same exact raw data set, and I said at 5 o'clock, please give me your final XYZ data set, I guarantee I will not have 2 data sets that are exactly the same, because it's going to be your interpretation of what the valid data is. And the more experience you have with processing the data and understand everything that's going on when the data is collected will influence how you interpret and process the data. All right? So it says, you know, there are hydrographic situations for which the algorithm inside Cube and inside of any auto processing program that it does not have sufficient information to make an adequate position. It's doing statistical analysis on what it thinks should be the best result for your data. All right? It is the operator's responsibility to ensure that these are recognized and corrected if required. You know, I know the AI and the machine, what's it called? Machine learning is it's on the uptake and things are getting better with it, but I still don't think it can think like we do. You know, and the more experience and knowledge you have with doing processing with multibeam data, and like I said, this is my 23rd year of doing multibeam, I still learn new things. And I look at things a little bit differently sometimes after I learn something new. So, you know, my interpretation changes slightly the way I look at things. So, again, it's your interpretation of what the final valid data is. All right. Other things that happen, sound velocity issues. Any sonar manufacturer that's sitting in here, please don't shoot me. But if you have a flat array, you know that a sound velocity probe at the sonar head is required for you to generate the slant ranges. All right? Why do you not include it with the sonar when you sell it? Because the first thing you do and you tell the user, oh yeah, our sonar's $95,000, but you need to buy the $6,000 sonar probe with it, or sound velocity probe as well. Why don't you just say it's $101,000 and it includes a sound velocity probe? Because I cannot tell you how often I show up and there is no sound velocity probe at the sonar head, and they don't even have a sound velocity profiler. All right? And I'm like going, okay, we'll do the best we can, but I don't guarantee that the data is going to be valid. And, you know, these are what we're seeing is, you know, where we see this reference surface line nice and flat. If you've got, you know, a too fast or too slow sound velocity, then it's going to create these smiley faces or frowny faces. You know, so this is what's going to happen. I get data like this all the time, and I'm going, okay, well, it's definitely a sound velocity issue, and I can fabricate sound velocity profiles with the best of them and make the data flatten out. I don't guarantee that it's going to be accurate as far as its depth is, but I can make it look good. Last slide here, there are great advances on the post-processing of your position, motion, and heading data with the HYPACK SBET files, and now the other inertial systems, SVG and CODA, they have their ways of post-processing as well. And if you have the ability to purchase these other softwares to do this, I highly recommend it because it can really save your data. Did a survey over in England 2 years ago, and the RTK was in and out the whole time, and we were trying to do a patch test, and we collected the data, we brought it into the office, and we're calculating all the patch test values, and they were okay. I wasn't real happy with the way the overlaps worked out, but you know, this is what we got, and the guy from Planix was there. He post-processed the data that night, brought the SBET file in the next morning, and was in front of a class of about 12 people. We uploaded the SBET file, applied it to what we had already brought in with the patch test values, and now the data blended beautifully. And we got a little bit better values for all of our patch test values, and everybody was able to see how valuable this tool could be to their data. Right, one thing to be aware of with this post-processes, it does not replace the heave value. Everybody think it does, but the delayed heave is a completely separate piece of what this software can do. So HYPACK, inertia, the SBET files that are created from these programs, they fix position, motion, heading, and RTK tides. They do not change the delayed heave. That's, again, a separate piece. So if you have it, great. I ran into an instance also this past summer, or actually this past fall, where data was processed and we brought the SBET file in, and it made the data look like garbage. And I'm pulling my hair out. The guy at SBG is pulling his hair out, and he's trying to figure out what's going on. They thought they processed it correctly. I'm looking at it, and I took 2 of the files that ran opposite directions but overlapped one another to try to find some feature on the bottom so I could see just how much of a shift it was putting in the data. And it ended up being like, I forget what it was. It was like 30 meters or something like that. And I'm like, wow, 30 meters, that's a huge shift. And as I said, so how fast was the boat going? And like, well, about 2.5 knots. And so, all right, so I took the distance and divided by the speed. Okay, well, that's about this much distance, and that's about this much time. And I'm like, I looked at it and I go, well, in order to fix this, I need to apply about an 18-second latency to it. And all of a sudden, does anybody know what 18 seconds means right about now? What? Nope. Very good. Who said GPS time? Winner, winner, chicken dinner. All right. So they had processed the data using GPS time. All right. Almost everybody in the world uses UTC time for all of their timing. So I called Mike up and said, hey, Mike, in the inner hour difference box here where it says UTC minus local, I said, is that just integer based or can I put decimals in it? And he's like, oh yeah, you put decimals in it. I said, great. So 18 divided by 3,600 seconds in an hour, 0.005. I applied a 0.005 hour difference and the data was amazing because I applied this 18-second shift and now everything lined up like it should. Right? So just, again, it's one of these things. Be aware that you've plugged everything, processed everything correctly. We get the phone calls because we're the last thing that has the data. So it's got to be something we're doing. Well, it doesn't have to be. It could be. I mean, I'm not saying that we're not at fault sometimes, but just make sure everything up to the point you bring it into HYPACK is correct. And this was an instance where, you know, GPS time versus UTC time caused everything to go crazy. And again, we had the ability to apply the correct shift to make it all work. So anyway, that's the last slide, and right now that I've got for Multibeam tips or tricks, and if anybody's got anything that I didn't show and would like me to add, I'd be happy to. But these are all the things that I know we run into on daily, weekly basis in tech support at HYPACK. So like I said, I'm just trying to keep you from running into these types of issues. Sound velocity, what's the question about sound velocity? Huh? Did I talk about it? Yeah, like right there?
No, not like right there.
Yeah, Drew. Typically, the C++ runtime error usually has to do with the redistributables that Windows has, which I wouldn't be surprised if it's a Windows 10 that Microsoft didn't update at 7. Inside of, get out of here. Something to look at, Drew. Inside of almost every version of HYPACK, if you go to the support folder, there's this VC redistributable x64 and x86 executable. That's usually the C++ issue. If you'll just double click on it and run it, assuming you've got the admin rights on that computer to do it and ACID hasn't blocked you out, what this will do is it will reassign all of the C++ stuff that we require and reset it up on the computer. Then I would advise that you reboot the computer and let it reboot with these new redistributables and see if that doesn't resolve the issue. It's under the support folder. It's these two VC redisks. One's for the 64-bit operating system. The x86 is for the 32-bit. Yep, no problem. Anything? Yep, Corey? Well, where the heck were you? Okay. Okay, so, sure, yeah. So the question is how often should you do a patch test? Okay, that's, yeah. Yeah, simple enough question. So if I were going by the Corps of Engineers manual, its exact words is, I just it went out of my head, periodically, right, periodically. All right, does that mean once a week, once a month, once a year? My practice, once an hour, my practice was every survey. The one thing that's probably the most misunderstood about patch test is that it has to be done on your job site. No. Doesn't matter if you're here or Timbuktu. It's the orientation between your sonar and the devices that are measuring your yaw, pitch, and roll. All right? If I'm here or over there, your boat didn't change. All right? So if you've got a patch test site somewhere local that's got everything that you need, and that's the way it was when I was in St. Louis, it was 20 minutes from our office. We hooked the boat and trailer up. Off to that site we went, put the boat in the water. Took us 15 minutes to collect the 7 lines that we needed, back on the trailer, and away we went to the job site. All right? Knowing that everything was going to be the same when we got there. We'd come back. On our way back, we would just hit that site, do it again, just to make sure nothing changed over the survey. As far as repeatability for the values, the one thing you have to understand about the patch test is it's doing statistical analysis. It's looking at data. What would be really great, and John, I know you'll probably agree with this when I say this, is that the electronics on the board that are doing all the measurements of the yaw, pitch, and roll, that as close as possible, that they are as parallel and perpendicular to the box that they are bolted to. The simple thing would be is if I could shoot the 4 corners of that box in, and going with the assumption that the board that's doing the measurements are as parallel and perpendicular to that frame that it is mounted to, then that would be the other statistical way to try to get the offsets, because I can measure the 4 corners of the IMU and the 4 corners of the receive array of the transducer, and then I could do measure geometry to figure out what the offsets are that way. And I know a lot of people that do that just to get an upfront value. All right, then they'll go and do the patch test and see how much it fluctuates. Well, if you don't have the ability to do that, then that's fine, and you're doing repeatable patch tests. Typically, what I expect to see is anywhere from about 1 to 2/10 of a degree change from one test to the next. But our suggestion is you keep a running total and a running average. And what you'll find is after about 6 or 7 patch tests, that even though the last time you did it, you got 3.25 for the roll, and you get 3.35 this time, or 3.45, by the time you average that in, that roll value may change 100th or 200th on the average. And since it's all statistical, we suggest that you use the average value. Because it's all in the wash of you're going to get pluses and minuses, and in the middle is where you should be. And that plays some effect. Yeah, and no offense to this, John, but I got shanghaied one time out in the Gulf of Mexico in about 6-foot seas. And I told the company that had brought me out there, I said, I don't care how good you think the PAWS MV is, I am not doing a patch test in 6-foot seas. Besides the fact that, it was a long day. But, yeah, so you want to try to do it in as best conditions as possible, especially with the best positioning accuracy possible. Yes? Oh, sorry, I'll get back to you, Corey. No, go ahead.
There's obviously like a temporal impact on, I guess when the sonar pings and when it receives data back from the time lag between those, depending on how deep the water is. At what point do you apply different parameters like pitch, roll, heading, and position? Does it all happen at ping time, or does it happen at receive time, or does it happen at some?
Well, I guess each manufacturer is going to be a little bit different. I'm assuming I'd have to ask Mike how he's actually doing it, but the data comes in from the sonar, typically time tagged. Okay, so we assume that that is the correct time to use for that ping and its data. And what we do, and what just about every software that I'm aware of, is the ping time is the key. So if the ping time happened at 12 noon .000, all right, you're better off buying a winning lottery ticket than you are to ever expect that you will always get a position, a motion, a heading that happened at the same thousandth of a second that that ping happened. Because the range is changing all the time, which is changing the ping rate. And typically you've got position, motion, and heading coming in on a static, 20 hertz, 10 hertz, 50 hertz, whatever. So they're typically, 100th, 200th, 500ths of a second split apart on their time. You may potentially get, a ping that happens somewhere on that time, very close. But the ping time is held, and we need a position that happened before time and just after time, and we interpolate the position to the ping time. We interpolate the roll, the pitch, the heading, the everything to the ping's time.
Because you don't want to apply the roll at the ping time, then you want to apply the roll at the receive time.
And if that, I'm assuming that the time that's in the packet from the sonar is the correct time. Whether it's, I don't know, I don't honestly know if it's the ping or the receive. I'm assuming it's the receive. We had some users overseas that replicated one of our HSX files, that they were collecting multi-beam data in 200 meters of water at 35 knots. And it took Mike, our programmer, like 2 hours to figure out that it wasn't something that was actually collected. They somehow replicated our sonar data, and what was happening, the way Mike had always done it, was what he called the one-way travel time. All right? So at 35 knots in 200 meters of water, the swath was over 600 meters wide. At the outer beams, they were seeing that the outer beams were shifted 19 centimeters forward of the actual position at nadir. And what Mike explained to me was that it's not that sound has momentum to it, but it's the fact that the boat was moving as the sound wave was still being transmitted. And that when that ping happened, the outer beams didn't actually reach the bottom till when the boat was actually 19 centimeters forward of its position. But again, they simulated a file at 35 knots. All right, and at 35 knots, the position of the outer beams were only 19 centimeters forward. The footprint of that fully engulfed that 19 centimeters. So Mike sent out an email, Sam, this was before your time at R2, but he sent it out to Kirk, and he sent it out to somebody at Reese On, and he sent it to Brian Calder and David Wells and a couple of the brains at UNH, UMB. And he got 5 replies back. 3 of them said it should be straight out. Kirk was one of them. Said that when the R2 pings, it goes straight out. So you should use what we call the bore sight translation now. And the other 2 said, yeah, we agree with what you're doing with the one-way least travel time, that 19 centimeters forward and 200 meters of water. Yeah, that sounds reasonable, that's what happened with the sound wave. So he said, okay, well, 3 out of 5 say bore sight, so we now default to the bore sight as the default, but we do have the one-way least travel time as an option B selected in the editor. So, yeah, I looked at this. I had to zoom so far in. I actually went in and created a line file that went across. And I had to zoom so far in to see the 19 centimeter shift forward and go, okay, Mike, what's going on? He said, he said, man, it took me 2 hours to figure out we didn't collect this file. And he goes, they somehow replicated it, you know. And he goes, and you know, he told me the story about it. So, yeah, that's what can happen with the ping, the transmit versus receive. I'd have to ask Mike to know for sure. He'll be in here in the next session, so I would ask him that. Anything else? Okay, well, we're going to be done early for this by 15 minutes. You're welcome. Thank you.